Okay, uh, I hope I'm audible enough, and we'll wait for another 2-3 minutes for others to join, and then we'll start. So I think we can start now. So welcome you all to the 10th problem solving session for this course titled Principle of Communication Systems. So as we have already seen that the content of week 10 is an extension of the extensive discussion on probability theory in week 9. And actually week 10 content three very crucial things. First of all, I think you are already aware of it. You have seen the lectures. Is about Bayes theorem, and building on the top of that concept of Bayes theorem, which is really important, or Bayes rule, however you want to see it. You have seen two very fundamental receivers in our wireless system. Not only wireless system, it is kind of universally applied everywhere. That concept of maximum a priori probability, or MAP, and maximum likelihood, that is ML. So in wireless receiver terms we call it MAP receiver and ML receiver. So although the topics are extensively covered in the lectures, I will try to reiterate few things here just to make you remember things. And in the lectures, actually the concept of map and ML receiver is discussed through a binary symmetric channel, uh, which is explained in a very nice manner. And we'll also see its connection with the how it connects to the practical wireless channel, where I guess you have already seen that relay faded channel has a particular probability distribution, and how the presence of multiple paths leads to a power delay profile. So we'll discuss these things after if we are left with some time after solving the assignment questions. So Nilesh, I hope you can hear me, right? I just need a feedback here.
Yes, yes, you are audible.
Okay, okay,
Am I
thank you.
audible?
Yes, yes, you are, you are. Thank
Fine.
you, thank you. So let us start with our first question, which basically a theoretical kind of uh, query, that what is any subset of set of all possible outcomes of a random experiment is termed as. So I'll take this opportunity to briefly explain what this even means, even though it has been extensively discussed in the lectures. So you see, when you perform a random experiment, you are going to observe not a single value but multiple values, and which value will arrive at which time instant. For example, let's pick the simplest of the examples. You consider a coin toss as a random experiment, and you are not sure that what your outcome is going to be. It can be head or it can be tail, and it really depends on which time instant you are performing. So based on that your result changes. So random experiment basically means whose output is going to be random, and whenever the randomness comes into picture, the probability is a kind of indispensable idea in that context, because nothing is deterministic now. So everything is discussed in terms of probability. So when you talk about a random experiment, so let me write here random experiment. This implies that the output cannot be predicted, or in other words, not deterministic. So when you perform a random experiment, basically you can have multiple possible outcomes. And we denote the set of all possible outcome by a particular name which you are most likely you are aware of. It's called sample space of that particular experiment. So let's say if my experiment is I briefly discuss three experiment just to set the example here. Let's say I denote the single time coin toss as my experiment. So can you say what my sample space is going to be for this particular
Head and
experiment?
tail. Head and tail.
Yep, head and tail. So there are only two possible outcomes. So let us try to make things a bit complex. Not complex exactly, I just want to extend the idea. Now my experiment is two time coin tosses back to back. So
Then four outcomes.
four outcomes, right? For example,
Head,
head.
head, head, tail, head, tail, tail.
Correct. And similarly we can extend this for n times of coin toss. So you can see your sample space basically grows in size. For single time it's only 2, for 2 times coin toss it's 4, for 3 times I guess you will have a 3 factor, right, or yeah, 8, and like that it will go on. So
2
this is,
raised to n times.
yes, correct, for n times single toss it's 2 to the power n. And what happens, let's say it's except a coin toss, if you pick a cube which has basically 6 faces, and you can have any number between 1 to 6, then in that case what it's going to be the let's say the size of sample space when I toss the cube n times.
cube is outcome is 6 times if we are doing one.
Correct, 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 correct.
So
So if I do its n time, then it is going to be 6 to the power n, right?
yes.
Correct. So this is all about sample space. So sample space basically contains set of all possible outcome, or in other words, the if you talk about in terms of probability. So what is the probability of sample space going to be? Since sample space encompasses all possible outcomes, we can intuitively see that there is no outcome possible which is not covered in the sample space, right? And the probability is all about the mapping from the sample space to this line, like sorry, not line, interval 0 to 1. So let me write it down here. So let's say this is your whole sample space S, I denote it as S, and you are basically mapping it. You are not exactly mapping the sample space, you are like you can map whole sample space, no issues, but it's mostly about the subset from here. So this is the line 0 to 1. So this is what P is, that is probability function, and this is the mapping. So it's more like a mathematical formulation. You have a sample space which contain all the possible outcomes. In other words, any outcome that is possible is must be included in the sample space, and probability is all about mapping subsets from this sample space over this real line. Not exactly real line, it's an interval specifically between 0 to 1. And any subset of this sample space is what we term as event. So any subset E is termed as event. In the lectures, it's beautifully explained in terms of the pulse amplitude modulation, or PAM. So I'll just reiterate few points from there. So in the course, it's talked about 4-array PAM. So basically, you have 4 possible symbols.
So
4,
answer of previous question is event. Am I right?
yes, yes, event. So sample space contains the set of all possible outcome, and if any subset in the sample space is basically termed as a event.
Fine. Okay.
Yeah. So when I say subset, by the way, the sample space is itself also a subset of yourself. You can see it. So in that way, it's a event also. So when you basically map the whole sample space, so where it's going to which value to it's going to be mapped. Can you just
Now, will you please repeat the question?
yeah, like I'm asking that like probability is all about mapping a event to this like interval, right? 0 to 1. So what if I want to map the whole sample space? So what's the value going to be, or like, or what value
So,
exactly to it's being mapped to?
so if we do a sum of that probability, it should be a one.
Yeah, yeah, exactly. So probability of sample space, that is mean probability that of all outcomes, basically like any of them, right? So intuitively we can say it's going to be 1, because there is no outcome that is possible and that is not covered in sample space. So every outcome is there, every possible outcome is there. So the probability of that event happening is 1, because nothing is excluded from there, right?
Fine.
Yeah.
Yes.
So I was talking about 4 array PAM. So that means we have basically 4 possible symbols. So here the experiment is to basically the symbol generation, and we have 4 possible outcomes. I am writing in terms of the sample space only. You have minus 3 alpha, minus alpha, alpha, and 3 alpha. These are basically 4 possible sample points. And of course, event is going to be any subset of S. So you can just pick some randomly a subset. For example, this is a subset of the sample space. Hence, you can term is as some event. And the moment you make this event, the event is going to have some probability. And if I denote it as event A, so what is A bar is going to be? A bar is basically the complement of A. And in the words, if I want to mention, it is simply like not the sample points not in A. That's it's all about. So it contains everything that is not in A. So if I draw my sample space something like this, and this is my A here, this triangle, this is A, and this is my whole sample space. So my A complement is going to be the sample space except A here. So this is my A complement or A bar. So every point in S, that is sample space, except the ones which are in A. And this is a good point to introduce the idea of mutually exclusive events. Mutually exclusive means basically there is no common sample point between the two events. So you can see by definition itself, A and A bar are the A and A complement are mutually exclusive, and that's the kind of simplest example, because as per definition A complement contains the points that are not in A. So if A and B are mutually exclusive, then basically in the common they have no sample points, so that in mathematical term we denote as null events. So no common sample points. For example, if I just took these two events here, one is minus alpha and alpha, another is let's say 3 alpha, let us denote this event as A, this event as B, then you can see A and B has nothing in common, so this applies to them. So therefore these two are mutually exclusive. So let us move to our next question. It basically asks which is the following is not one of the axioms of probability. So this is a good point to discuss once again the three axioms of probability. So the probability is actually a measure. I'm not, it's implicit, so I'm not writing it really. The probability of any event, you can write set here also, A, satisfies three properties. So first one, first axiom is about the non-negativity. So the probability is not going to be negative. Second axiom says the probability of sample space is 1, and that is pretty intuitive because we have already discussed that the sample space contains all possible outcomes. So the probability of sample space happening, that means probability of uh, the event, uh, one of the outcomes is happening is 1, because once you perform the experiment, one of the possible outcomes is going to be appear. We don't know which outcome, but one of them at least is going to be appear, and sample space contains all of them. So the probability of sample space itself occurring is 1, because although the experiment is random, basically the experiment is random means your output has multiple options, so in that way your output is random also, but some output is coming that is deterministic, and sample space exactly contains all outcomes. So the probability of sample space is other way of saying probability of one of the outcome is coming, and that is deterministic. What is coming out there is random, but some outcome is there, it's deterministic. And basically probability 1 means it's a deterministic thing. You can intuitively see that, for example, if you take an example of single coin toss, when I say that probability of head and tail in case the coin has no bias, so you can say that probability of head is 0.5. So what does that mean? uh, when I say that P of head is 0.5, that means with 50% probability head will occur, but there are also 50% probability that head won't occur. But probability of head and tail occurring, I mean any one of them, is going to be 1, right? Because the moment you toy in a cause, the moment you perform an experiment, it is deterministic that either either head or tail is going to be occur. So even though the output is random, the fact itself that output is happening is deterministic, and that is why probability 1 suggests. So first and second axioms are pretty straightforward. The third axiom, I would say, it's a bit not so straightforward. It says that probability of A union B, that is basically covers all the points in A and B set, is equal to probability of A plus probability of B, given A and B are mutually exclusive. That means they are not having any common sample points. In other words, their intersection is basically null event. So to prove this first axiom, you can see the whole sample space can be written as any event A times its complement, right? Because we have just seen in the previous slide here that you pick any event A, for example it's this triangle here, and A complement is going to be the points that are in not A but in sample space. So you can see if you combine A and A complement, that covers the whole sample space, and they are mutually exclusive, so there is no common point. So if you take the union of A and A complement, it's going to be always the whole sample space, no matter what the event is going to be. And by definition, their intersection is the null event. So you already had from the second axiom that the probability of sample space is 1. And from the third axiom, we have this: if A and intersection of A and B is null event, then we have probability of A union B is equal to P of A plus P of B. So these all suggest that probability of A plus probability of A complement is 1. Probability of A complement is 1 minus probability of A. But we already know from the first event that probability of any event is going to be non-negative. So if this is non-negative, that means probability of A is going to be less than 1. So if we combine these things for any event A, it is going to follow this, that is, probability is always going to be between 0 and 1, no matter what the event is going to be. We next, even if the phi is a null event, so that probability need to be intuitively 0 only, but still it need to be validated via these axioms. So we can see the sample space can be written as sample space union null event. Actually it doesn't apply for only null space. For any event, if you take the union with null event, so basically that will the event will remain the same, because there is no contribution from this null event or the null set. And similarly, if I take the intersection of that null event with the sample space, that is going to be null event only, and that applies for like in place of S, if you can replace with any event, the results will remain same. So we have already seen that probability of sample space is 1, which is now equal to probability of S union null event, because we have already seen these two sets are same only, and since they are mutually exclusive established by this one here, result here, I just can write them as individual probabilities. So now this is here is 1, so this implies probability of null set is 0. So now let us look at our question here. So the first one is the first axiom. Second one, for mutually exclusive events, this is this P is equal to PB. Well, this is not a part of axioms, because even if you don't know axioms intuitively, you can see this. If you know about the mutually exclusive events, you know that A intersection B is going to be a null set, right? And we have just seen that probability of null event, sorry, it's not null set, it's null event. Actually you can say both. Probability of null event we already established, it's 0. It's not PA times PB. So this is not a part of the axioms. The third one is the second axiom here, and the fourth one is the third axiom. So it's the second one which is the not one of the axioms of the probability. So let us move to our next question, which basically asks that which if two events are mutually exclusive, then which of the following statement is always true?
So both are the mutually exclusive. That means probability of A subset B is equal to 0, right? The 4 is the correct answer.
Yes, yes, probability of A intersection B is going to be 0, because whenever I say mutually exclusive, that means there is no common
No
sample
common.
points between them.
Yes.
Yes, so that means
It's null set.
yes, it's a null set, and the yeah,
Probability of null set is 0.
yes, it's always 0. So the fourth one is the correct answer. So now it's about the conditional probability question. So first I need to define what conditional probability even is. So let's say if we have two events A and B, two events A and B, and when I write P of actually the idea of conditional probability is kind of very interesting, not only from the maths but more like intuitively you can say. First of all, when I write P A dash B, it means probability, or better to say conditional probability, conditional probability of A given set B. So before giving the answer here, I would just like to let's pick the single time coin toss experiment. So let's say my experiment is a single time coin toss, and I am denoting the event A as the set containing H only, that is the head, and the event B, which is the event tail. So probability of A given B, that is the conditional probability of A given that B already happens. So even before knowing what conditional probability is, can you guess here what is the going to be answer here for this particular experiment and this particular choice of sets A and B?
That is the tail. Probability of B, that is a tail happened. Then what is the
Yes,
probability of H? This is
yes.
again 50%.
It's actually a single time coin toss. So you toss the coins once. You already know that the event B has happened, that is the tail. Now, what is the probability of the head,
So
the event
next
tail?
time it will be a tail or it be a head.
No,
So
it's actually there is no next time because the experiment is single time coin toss only, right? So
okay.
yeah, can you just think a little bit? You are on the correct track, but don't think about the second time. It's like I am talking about the experiment is itself about a single time coin toss where A is
So
the
100%.
yeah. So yeah, so you are saying
One
no. Your B already happened na, so till
tail is happening. Then what
yes,
is the probability of head is happening,
yes,
right?
yes.
Mm, 0.
Yes, it's 0 because if it's a single time coin toss
And
and if
already.
yes,
Hmm.
you already obtain the tail, so there
Yeah.
is no head is going to be, the probability is going to be 0 basically.
So if you are two time, then it should be a 50%, right?
Okay, let's check that also. If it's a
Okay.
2 time, as you said, 2 time coin toss, then the event cannot be single H and T. Let's pick something else. Let me pick something A is equal to first head and then tails, and the event B is let's
So
say
I am just that it first time if you are getting tail, then what is the probability that second time we are getting tail or head?
okay, you are like okay, you got first time tail, but then in like while I'm having the sample space for two time coin toss, any event I need to include both the results, right?
Yes.
So
Okay.
I cannot have a yeah, single one. So I understand your question. I will come to that also, but let us first cover this one. Then I will answer that.
Okay, no issue.
Yeah. So let us answer this for this particular question, that the A is the probability that in the first toss you obtain head, in the second toss you obtain tail. I'm sorry, A is not the probability, A is the event, and the B contains two events. Sorry, B is the event. It contains 2 points. First is, in the both the cases it's head, and in the second case its first case is head and second case is tail. So let's say the head and tail probability are zero point 0.5, that is the coin is unbiased. So can you intuitively say what your probability of A given B is going to be in this case? You already know that B had happened. That is, the event B has happened. That means one of the sample points in B has already taken place. So with that knowledge, what is the probability that you can infer that A had happened? I'm not at all talking about math formulas here, just pure intuition.
50%.
Yeah, and how do you reach the conclusion?
Um, because B is having head, head, and head tail.
Yes.
What is the probability of A that it should be a head and tail? So once if it is a head, head, or head and tail, so one it is a both half probability. 50% probability that second time we'll get headed or head and tail.
Okay, correct. So it's like 50%, right? 50%. Now let us make the B it more interesting. I'm including other points also. That is first tail, then head, and then it's tail and tail. So basically B here is a sample space, whole sample space. You can see
So
all
one
four
divided by four, that is a 25%.
25%. Correct.
Am I
So you can see condition your in this case, like when you basically knowing sample space means nothing at all, right? Because in that case it's kind of irrelevant, because sample space is anyway going to happen. But when know that B is some subset of sample space, that is in the first case when you have only these 2 points, you can see that probability of A actually increased, right? It was 50%. What I'm trying to say, like if while in
Yes.
the second case B contains all the points, right? That is its
Yes.
whole sample space, and the conditional probability of A given B, like given sample space, doesn't make much sense because sample space is anyway going to be there. So in that case your probability was only 25%. But the moment you know that that B contains only 2 points and B happened, then you can say there is an increase in probability
True.
for this
Agree.
particular A. Yeah. And to answer that question of yours, that what is like in first coin toss you have a tail, what is the probability in second coin toss you are going to see tail or head, right? So it's a, if it's an unbiased coin, it's not going to influence the result, whatever being the result in the previous time instant, right? Even if I have, let's say 500 coin toss before, and whatever the result is on 500 1th time when I toss the coin,
50%.
yes, it's unbiased still, so it's going to be again
Yes.
50% head, 50% tail. Yes, but if you talk about one particular sequence like head, head, tail, 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 head, head, then the probability changes.
Yes.
But if I am looking about individual, like at every time you toss it, then the probability remains same irrespective of whatever happened before or what is going to happen. But yeah, if you talk about a particular chain of sequence, then it changes based on what you really want. So probability of this conditional probability, let me write the maths expression now, how it is being done. So probability of A intersection B, that is the common sample points, divided by P of P. Now you can connect the results from here to here. For example, you can see for single time coin toss, A is equal to head, B contains only tail. So what is my A intersection B is going to be in this particular case for single time coin toss? That is no common between them, right? So it's a null set or null event, and it's,
0.
yeah, its probability is 0. So if you use the formula, you get 0. Similarly, for second time two time coin toss, let's consider the first part when B contains only these two part. So what was that? What is the common thing between A and B here?
HT.
HT, right? So let me write it down here. A intersection B was this HT thing. And what is the probability of B there? Because B contains these 2 points, all possible are 4. B contains these two, so probability of B was, okay,
50%.
yeah, probability. So here it's like probability of HT divided by probability of HH and HT. So this probability here only is 0.25, right? If I talk about one particular possible T, and this one here is 0.5. So you can have the thing, you can see it's 50% as you have already obtained here when you make the math here.
Mm. Yes.
And now if in the second case when I said that H contains actually all the points, then you keep adding TH and TT, it effectively becomes the sample space only, right? So what I can write here, probability of the,
Mm.
this doesn't change, right? This will still remain 0.25. What will be here?
1.
Yep.
1.
Yeah, so you are left with probability of 0.25, so only 25%. So you can see actually both of them are matching no matter what your case is going to be. So this is what conditional probability is. It's actually very interesting. You need not know the formula of this particular maths here to find the conditional probability. You can find via intuition, and then when it comes to doing math and all that for more complex cases, you cannot really apply intuition for complex cases. It's easy to do it for this kind of things, but when multiple events and multiple things are involved, it's increasingly difficult. Then actually these things will going to help you.
So answer is 3.
Yep, answer is 3. So just a quick question here, if I can write that P of A given B is equal to P of A intersection B divided by PB, then what is going to be P of B given A? How can I write it?
So upper portion is same. In lower portion, probability of A.
Okay, numerator will remain same and denominator will just change. So from these two expression, can I write this thing? Just see once. Probability of A times probability of B given A times probability of
Yes, same.
B given probability of B A given B. This I can write, right? Because both are equal to probability of A intersection B.
Yes.
So this is actually fundamental to this base rule, where you can actually use this very interesting property. Apparently there seems no connection between them. This is the probability of event A, this is the probability of conditional probability of B given that A has happened, at is equal to just its opposite. So it appears there is no connection between them, but it actually there exists, and this can be exploited very beautifully as is done in the lecture. So maybe uh, I can discuss a bit base rule here only. Just a minute, I'll introduce a new slide here. So if I have a whole sample space like this, again this rectangular box kind of thing, and this side I am calling it a event A, and this side, this is what I am calling, not exactly I am calling, it's a complement, and this whole thing is sample space. So you can see already that by definition that intersection is going to be null set only, but even more interesting that a union A, it encompasses the whole sample space, right? So when these two properties are satisfied, A and A complement are mutually exclusive. So for A bar, that is A complement, these two are satisfied by definition, but this can be extended to any A B. You find two event A and B where the intersection is null event and the union is the whole sample space, then also your A and B are going to be mutually exclusive. And let's say if mutually exclusive and exhaustive. The exhaustive terms comes into picture because you can see that A and B combinedly, it should, let's make it A, let's make it B here. So let's make it B. Okay, so you can see A and B in a combined manner exhaust the entire sample space. What I'm trying to say that if you take A union B, so it covers the whole sample space, but there is no common sample point between them, so that is why they are called mutually exclusive and exhaustive. So whenever A and B are mutually exclusive and exhaustive, you pick any third set B, any third set C for any set C. Your C intersection with A and C intersection with B are also,
Null event.
no, they are also mutually exclusive actually. C is some other event, C is some other event. Let's say I am drawing a circle here in the purple. So let's say C is this particular circle. It is a subset of
Oh,
sample space, of course. So whenever you take C intersection with A, it is about this part, right? Let me,
got it. So it is a mutually exclusive but not exhaustive, right?
yes, not it is not exhaustive. It is not exhaustive,
Fine, got
but
it, got it,
yeah.
got it.
So these two particular sets are mutually exclusive, but they are not exhaustive because in a combined manner they are not covering the entire sample space. They are just
So this
covering
will happen only if and only if A and B are mutually exclusive and exhaustive.
yes, yes.
Otherwise, this is not possible, right?
Just a moment here. Um, for this, like you are asking for this to happen, right? C intersection A and C intersection B, right?
Yes, yes.
Okay.
They
For
are only mutually exclusive if A and B are mutually exclusive and exhaustive. If it is not exhaustive, then this will not true, right?
no, no. Actually, if they are for this to hold, they need to be, the exhaustive property need not to be there. They can be mutually exclusive only,
Okay.
and that would be sufficient, right? And just let me try to find a counter example for that, if there exist any. So let's say even if A and B do not cover the whole sample space, uh, then also C intersection A and C intersection B are going to be exclusive only. Yeah, as far as
So,
I can see, yeah.
so in one square box, we have a, let's say, multiple A, one B and C is there,
Okay.
and then A, B and D is there. Then we if we take a subset C and S subset B, C subset B, then is a mutually exclusive. If A and B are mutually exclusive, not require exclusive exhaustive.
Yes, 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 correct. And when I take the union between these two set here, that is C intersection A union with C intersection B, we basically obtain the set C.
Yes.
So now let me apply the some probability axioms thing. So if I apply the probability measure on both sides, we'll have P of C is equal to P of C intersection A plus probability of C intersection B. And this is because from the third probability axioms, if they are mutually exclusive, you can just separate them up and take their probability measure. That you can do. And we can extend one more step. This is probability of C intersection A. This can be written as probability of C, conditional probability of C given the A has happened, times probability of A plus conditional probability of C given B has happened times probability of B. So probability of C can be written in this form when A and B are mutually exclusive. So now I want to find the probability of C intersection A. Oh, sorry, this I have already written, but this is only one expression. Probability of conditional probability of C given A times probability of A. But this can be also seen from the other way around. That is conditional probability of A given C times probability of C. This is also another way of writing. And probability of C intersection B. Similarly, we write conditional probability of B given C times probability of C. So from this expression here, we can write probability of A given C is equal to probability of C intersection A, which can written in this form, probability of C given A times probability of A and divided by probability of C. So this whole thing comes into the denominator. Similarly, if I want to find probability of B given C, we can have probability of C, conditional probability of C given B times probability of B, and similarly this whole things comes here. So these two things are actually very nice this is actually whole thing is a Bayes theorem, and these are termed as a posterior probabilities. I'll try to explain in an intuitive manner what they actually are. Let me write down the terms. And probability of A and probability of B, this we call as prior probabilities. Prior probabilities. And probability of C given A and probability of C given B, this we denote as likelihoods. Likelihood. So why it's calling a posterior? It's because it is actually easy to make you understand using the concept of binary symmetric channel. Okay, we'll come to that later. So you can see probability of conditional probability of A given C, right? So this is calling a posterior probability. It's like the C event you already know has happened. Now the given C has happened. what is the probability that event A has happened. So you can, as of now I will explain later in terms of binary symmetric channel example, which is really nice, but as of now you can see something like that, the C is something, some event that happens later, and A or B were some prior kind of events which happened before C. So when I try to consider the probability of event A or probability of B, they are called the prior probabilities. They are being called the prior probabilities. And next come the likelihood. So likelihood, you can see this is the probability of C given A and probability of C given B. So it's like what is the probability of C event taking place given A has happened or B has happened. So why we are calling it exactly likelihood? So you can see this can correlates with the idea that what is the likelihood that the C is going to happen given the knowledge that you know that A has happened or B has happened. That is why it's called likelihood. And when it comes to a posterior probabilities, it is called posterior because you can see here the condition event is conditioned over C. So it's like the experiment is being performed, the event C has already happened. Now given the knowledge that C has happened, what is the probability that A was A has happened? So you can see there are two way around. First one is there is prior probabilities, which is the standalone probabilities of event A and B. Second one is likelihood, and a posterior seems like opposite. Like likelihood is all about that you know that given the knowledge of either A has happened or B has happened, so what is the probability that C is going to happen? It is a as if you are seeing from the perspective of before the experiment has happened. So you already know whether the A or B had happened. Now you want to find the probability of C happening. And the a posteriori is something like that after the experiment. It is like you have already observed that C has happened. So now given this knowledge, you are trying to predict whether the probability of what is the probability that A is happening or the B is happening. So this is what these three probabilities are very fundamental. The prior probabilities and likelihood and a posterior probabilities. These three are connected by this Bayes theorem, which is like very important, and I will try to explain in terms of binary symmetric channel, which is also explained in the little lecture. I guess that would make the things more clear from that perspective. So let me just briefly write down the generalized version of Bayes theorem, because this is where I am assuming that there are two sets only A and B, but in practice it need not be like that. So let me just draw a slide here. Okay, just one thing about the exhaustive thing I need to make clear, that even if it doesn't satisfy the exhaustive property na here, then these C intersection A and C intersection B are going to be mutually exclusive. But for this thing to hold, A and B need to be exhaustive also. I hope I didn't make this point clear earlier, so I just want to make it now, that for this to hold, they need not A and B need not to be exhaustive, but for to write C as this, that A and B need to be exhaustive, because you can see, for example, let's pick the next slide here and try to draw an image. Let's see, this is what A is and this is what B is. So this one is A, this one is B, so they are mutually exclusive, you can see. And this is what C is, let's say this is C, and this part here is what is C intersection with A, and this part here is what C intersection, sorry, C intersection with A it should be, and this is what C intersection with B. So you can see here that even though that C intersection A and C intersection B are mutually exclusive, but you cannot write this C intersection A union C intersection B is whole C. No, it is not, because you can see that this part will be left open. So, sorry, this part is not going to be covered. So this part to be covered, A and B need to be exhaustive, then only I can write this. I just want to make this point clear. Even if these two are mutually exclusive, to write this, that they exhaust C, to exhaust C, A and B need to be exhaustive also, apart from being mutually exclusive. So with that, let me delete this first. So just a brief, this thing generalized Bayes theorem. So instead of now A and B being mutually exclusive and exhaustive, let us consider A naught, A1 up to A n is there. These are all events, A naught, A1 up to A n. So there are total n plus 1 events. So these are mutually exclusive and exhaustive. That basically means you pick any two things, AI and AJ, their intersection is going to be null event, and the union from I is equal to 0 to n of AIs is going to exhaust the entire sample space. So in this scenario, we have already seen that probability of set C intersection with AI can be written in two ways. One is probability of AI given C times probability of C, where this is the a posterior probability, or we can write it as probability of C given AI, which is the likelihood, times probability of AI, which is the prior. So we are finding interested in finding the a posterior probability usually, which is given as P of AI given C is equal to P of C times AI times PAI divided by P times C, and we have already seen that how to write P times C. It's the summation over I is equal to 0 to n probability of C given, sorry, let us make it J. J tends to 0 to 1. This is the likelihood and this is the prior. Prior of AJ. So see, this is again I am writing here posterior probability, this is prior probability, and this is likelihood.
What is the meaning of a posterior?
A posterior mean, in the sense, actually it would be clear when I discuss the binary symmetric channel based explanation, but a posterior means it's like after the event has happened, you are trying to detect the probability of like the event that might be a cause to it. So it's like see something that is the output of the experiment, right? So you have already seen the result. It's like you have already seen the result. Now based on this knowledge you want to predict which of the event triggered this result. Am I able to explain that?
Yes. Yes. Yes.
So there are two way of looking at it. First, before the experiment happened, you can compute the likelihood, which is this one, that you know which of these AIs has happened. No, like it's not actually the knowledge of which of the AIs happened, and this is the probability of likelihood that okay, if AI has happened, what is the probability of that you are going to observe this particular event from the experiment. This is the way of seeing likelihood before the experiment has happened, and after that is happened, so you now compute a posterior probability. Now you have the knowledge what has happened, and based on that knowledge you want to compute which of the uh, input is most likely to trigger this event. And when you try to maximize the likelihood, it's like maximize the likelihood in the sense sometimes you want to see like for which of the input the probability of output is most. So there are two ways of looking at it. First is you try to maximize the likelihood. For example, there are I is equal to 1 to n. You compute this conditional probability of C given all AIs, okay, from I is equal to 1 to n, and which one of the probability of I is max. So you basically choose that AI, that okay, given I choose this particular AI, the probability of C is going to be maximum. And the other way around is that once you have the knowledge of the event C, you want to see which one of the AIs A1 to up to AN is most likely to trigger it. So when you maximize the a posterior probability, it's like you have observed the event, like what has happened. Now you want to see the probability, like probability of the event which has most likely triggered it. So that is the
So
concept.
we can say in similar way that we are transmitting something, we are receiving something.
Yes.
Now we are finding what is happening in the channel.
um, what is happening in the channel in the sense
So what happened in the channel that my transmitting signal is not received as it is. It is with some distortion, with some noise. So we can find the noise in the channel,
Okay,
kind of thing.
not exact. It's mostly like, for example, you are transmitting 0 and 1, right? You don't know which one you have transmitted. At receiver end, you receive something. Okay. Now, based on that knowledge, you want to find the probability, a posteriori uh, probability that given this knowledge, what is the probability that 1 is transmitted and what is the probability that 0 is transmitted, and which one is the maximum. Given this knowledge, you choose that.
Okay.
Yeah, so I guess this part would be a bit more clear when I explained it's based on symmetric channel. So let us move into there. So you actually
If,
pointed
if
out
you take some examples, then it will be clear maybe.
yes, and actually you actually pointed out this very good question, like yeah, this maximum a posterior probability and maximum likelihood are two receivers basically used in communication systems. So I'll explain them now. That's a good point here. So let us do that. So let us now briefly talk about our channel modeling here. So we'll talk about binary symmetric channel. Binary symmetric channel. So this is transmitter end and this is receiver end. So let us denote the event A naught, that 0 is transmitted here, and let us even denote the event A1, that is 1 is transmitted. So when you transmit 0, with some probability it is being received as 0 as receiver. So we denote the event B here, which is the receiver output, and B being 0 happen with some probability, right? So let's say that probability, first of all we denote the probability of, like 0 can also be received as 1 because of, you are, as you are saying, because of something happened in the channel or noise. So there is a possibility that you transmitted 0 but you receive it 1. Just a moment.
So both the probability sum is 1.
Yeah, that is what is called as the flipping probability or the error, channel error probability. Let us denote it as p here. So it's the,
1 minus p.
yes, it's p, so this should be 1 by, sorry, 1 minus p. And here let's say I pick the probability 0.2. So you can see this is the likelihood, right? And this is 0.8. Likelihood in the sense, if I go back to the expression here, okay, just a moment. Yep. So this one I called likelihood, probability of C given A. So you can connect it here. So this is the probability of receiving 1 given 0 has happened, right? So this one and this one, they are both likelihoods. So you can see this is the, this one here, this line, this is the probability of B being 0 given A naught, that is 0 is being transmitted. So this is likelihood if you compare with this expression here. I told you earlier that C is something you observe after the experiment is happened. Here the experiment is the transmission, and AI is something that has triggered it. So if you connect it here, A0 is something that is triggering it. A0 is a triggering event which is basically transmitting 0, is what I am calling the triggering event. And this is the probability that B is 0. So given the knowledge that you have transmitted, what is the probability that 0 is going to be received? So that is what zero point 0.8 is. So that is one likelihood. Similarly, what is the,
Got it.
yeah, and similarly what is the probability that B is 1 given the knowledge A0 happened? And when I say A0
Point
happened,
2.
basically means 0 is transmitted. Yes. So these are likelihood. So these are basically likelihoods, both these things. And the same concept apply from here also. For example, you are transmitting 1, so I am keeping the false probability or the flipping bit probability same in the both case, just to the for sake of analyzing it. And this one is again 1 minus p. So in terms of probability, you can write it as probability of B is equal to 1 given A1. And similarly here I am just not writing it because it will become too messy. So there is one thing remains. So this is one likelihood is now fine, no issues. What about the prior probabilities? I discussed here prior probability is a standalone probability, this P of AIs. So basically it is the triggering event. So here the triggering event are those things, right? So let us pick the probability of A naught.
So it is a probability of transmitting between 0 and 1.
Yeah, like it's like with what probability you are transmitting. Let's say if you want to be
0, yes.
unbiased, you then unbiased in the
50-50%.
yes, but it need not to be always unbiased. For example, if I pick it like this, that P0 I denote as the probability of A0, it is 0.2, let's say, or let's say 0.3, make it 0.3. And here I make P1, which is the probability of A1, as 0.7. So with 30% probability I transmit 0, with 70% probability I transmit to 1. So I'm less likely to transmit 0. For example, if I just make a crude kind of approximation, every 100 times I transmit, roughly 70 times I end up transmitting 1, and 30 times I end up transmitting 3. So these are known as prior probabilities. So these are known as prior probabilities. And this knowledge, probability of A naught given B or the probability of A1 given B, is what is known as a posterior probability. So basically you have seen what B is, that is essentially you have seen what the received bit is. Now based on that knowledge you want to find what is the probability that A0 is transmitted, that is what a posterior probability of A0, this P A0 given B. Similarly, given B, you are trying to find what is the probability that A1 is transmitted, and that is what the a posterior probability of P of A1 given B. So let us
Got the
just,
point.
yeah, so let us just put the maths here now. Let me introduce a slide here. So if I am willing to find probability of A naught given B, so according to the formula it's conditional probability of B given A naught, that is the likelihood, times probability of A naught, which is the probability of transmitting 0, divided by probability of B, which can be written in this form: probability of B given A naught times probability of A naught plus probability of B given A1 times probability of A1. So let us put the values. This is probability of B given A naught as 0.8, and probability of A naught is 0.3, and here I have 0.8 times 0.3 plus this is the likelihood of, this is the error probability, so that is 0.2 times 0.7, so it becomes 0.24 divided by 0.24 plus 0.14, that is 0.38. So it's 12 by 19. Okay, 12 by 19. Fine. By the way, here when I say B, I mean B is equal to 0. That is 0 is received. And also let us come, so this is the probability that 0 is transmitted given 0 is received. Similarly, compute the probability of A1 comma B. So this is basically the probability that 1 is transmitted given 0 is received. So here it should be conditional probability of B given A1 plus probability of A1, sorry, multiply A1 divided by again probability of B given A0 times probability of A0 plus probability of B given A1 times probability of A1. So the denominator remains same, it's 0.38. The this value is probability of B given A1 is 0.2 and this one is 0.7, so it's 0.14, so it's basically 7 over 19. So you can see after this 0 is being received, what is the probability of 0 being transmitted? It's 12 over 19. And what is the probability that 1 is transmitted? It's 7 over 19, right? So therefore probability of A naught given B is greater than probability of A1 given B. So what the receiver is going to decide in this case? What do you think? What is being transmitted, 0 or 1?
Am I audible?
Yes, yes, you are audible.
Fine, fine, okay.
Yeah,
So this
so
is clear actually. This is clear.
okay, so I just want, yeah, I just wanted to ask you, like, what you are going to decide in favor for. Like, for example, you know 0 is transmitted, you compute the probability, what is the, uh, uh, sorry, you know that 0 is received. Now you compute the probability, what is the probability of 0 is transmitted, you find that to be 12 over 19. And you also compute the probability, what is 1 being transmitted, and find it to be 7 over 19. So, what are you going to choose in this case?
So 12 by 19, that means probability that 0 is transmitted given 0 is received
Yes.
is more than probability that 1 is transmitted given 0 is received.
Yes. So what are you going
So
to
noise
choose?
is less.
Um, Sorry, I didn't hear you.
That means the probability of 0 transmitters giving 0 is received is more than probability that 1 in transmitted given 0 is received.
Yes, correct, correct.
So the channel is less noisy for 0.
Uh, it's not
It is not
exactly.
flipping the bit
No, no. It is some. It like sometimes it will flip the bits. It.
with the probability of 7 by 19, right?
No, 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 no. It's like, see, for example, if I go to the, if you talk about the flipping of bits, so that happens with the probability zero point 0.2. For example, if you transmit the 100 bits, 20 of them going to be flipped. So in this case we are not really worried about noise. What we are worried about is that in the receiver end you receive something. So you have your decoding process and you decided that 0 is received. Now the understanding we want to have here, that 0 is received, so what is the probability that 1 is transmitted or 0 is transmitted? So based on that the receiver have to make one decision. So that noisy part and all that will be covered in this flipping probability here. For example, if your channel is a lot noisy, then this probability will keep on increasing, like for example zero point 0.3, zero point 0.4, or maximum it will reach up to 0.5.
Okay.
So here we are concerned about like in terms of pure probability, like for example receiver have to make a decision here. So I'm asking you, like, what decision the receiver is going to make. Like the 0 is being received and it computes the a posterior probability of for both 0 and 1. It turns out that probability for 0 is more, I guess, because it's 12 over 19 compared to 1 which is 7 over 19. So what should receiver decide, that 1 is transmitted or 0 is transmitted? So actually receiver is going to decide that it will take 0, because the a posterior probability of 0 is higher compared to a posterior probability of 1. So if a receiver work on the principle of this maximizing a posterior probability, so let me write it down here. If the receiver works on the principle of maximizing the a posterior probabilities, this is, first of all, it's termed as a map receiver, and it has observed that probability of A naught given B is 12 over 19, which is greater than probability of A1 given B, which is, sorry, this is 19 here, and this is here is 7 over 19. So the receiver is going to decide in favor of 0. So receiver will decide on favor of 0. Because why? Because the way the receiver sees, the a posterior probability of 0 is more. It's like more likely 0 is being transmitted rather than 1. Am I able to make clear this point, or it will, like, don't hesitate to
Yes,
ask me
yes,
for.
yes, yes.
So the question you are putting about the noise is also correct, but that is actually covered in the error flipping probability. And
Okay,
okay, and here we are concerned about that. Okay, this map receiver works on the principle of maximizing the a posterior probability. That is, it has already received a 0. Now it would like to weigh the probabilities, that what is the probability that what is 1 is being transmitted and what is the probability 0 is transmitted, and whichever is higher, it is going to decide on favor of that. For example, in the lecture also slightly different values are used, where actually, if I am not wrong, uh, these prior probabilities are taken differently. In the prior of 0 is taken as 1, whereas the prior of transmission of 1 is taken as zero point 0.9, and in the lecture it is actually shown that a posterior probability is 1 is higher. So even if 0 is being received, the map receiver is going to decide on favor of 1, that is, it will decide that 1 is being transmitted, simply because the probability, a posterior probability of 1 being transmitted will turn out to be higher if you see the lecture. So map receiver is going to do that. And similarly,
okay,
there is another kind of receiver which is maximum likelihood receiver. I will take this opportunity to discuss that also. Maximum likelihood, or ML receiver. So ML receiver works on the what principle? It works on the higher likelihood probabilities. So what I mean by that, we have seen our likelihood probability of B given A naught, where B is equal to 0, is 0 0.8, right? That given 0 is transmitted, 0 is being received, is the probability is zero point 0.8, which is greater than the probability that 0 is received given A1 is transmitted, which is also the bit flipping probability or the error probability, which is 0 0.2, right? So maximum, if the receiver is working on the principle of maximum likelihood, it is going to decide on favor of 0 also in this case. So this is what likelihood of 0, and this is what of likelihood of 1. So in this particular example that I discussed here, both maximum a posterior probability or map receiver and maximum likelihood probability or ML receiver, both are deciding on favor of 0. But if you go through the lecture, you will see that map receiver actually decide on favor of 1. And the single most important difference between the maximum likelihood receiver and the maximum a posterior receiver is that ML receiver doesn't take prior probabilities into account. So you see here, it's only concerned about the likelihood, doesn't involve prior anywhere. So it does not take prior probabilities into account. So when your prior probabilities are equal kind of, then maximum likelihood. So okay, let me discuss three cases. First of all, when the prior probabilities are all equal, in that case maximum likelihood receiver and map receiver becomes the same. You can use the math and you can find it. So in that case you can use the maximum likelihood receiver. It's actually a bit less complex. But the moment the prior probabilities are going to be different, for example the one that is being discussed in lecture, that is probability of 0 being transmitted is 0.1, that is only 1 in 10 times, and probability of transmission of 1 is at zero point 0.9, that is 9 out of 10 times it is being transmitted. So in that case, the more unequal the prior probabilities is, the more important it is to use maximum a posteriori probability or map receiver to minimize the error in the receiver, because the maximum likelihood receiver doesn't minimize the error at the receiver end. It's what something map receiver does. And since maximum likelihood receiver fails to take prior probabilities into account, the moment the prior probability changes, the performance of maximum likelihood receiver is suboptimal. So it's the map receiver actually that minimizes error probability at receiver, but ML receiver doesn't minimize the error probability at receiver, and the performance between them we can see the gap will increase as the priors become more uneven. The prior probabilities, when they are more uneven, the gap between the map receiver and ML receiver are going to be high. You can see intuitively in the other way like this. So if I just go to this, this is this is the probability of B, so you can kind of ignore that. So this here is the a posterior probability, so you can also see that a posterior is proportional to prior times likelihood. So when priors are all equal, a posterior is, you can see, is proportional to likelihood. That's why their performance is same. But the moment prior are unequal, then the prior will start influencing, because a posterior is kind of prior times likelihood. So that is the intuitive idea behind the map and ML receiver. So now let us briefly solve few of these questions here. First of all, it asks about the quantity probability of A union B can be expressed as follows. Okay, so this is a nice question which can you can use actually the graphical method to easily solve. So let us say this is what A is and this is what B is.
So answer is B. Answer is 2.
Answer is first of all this is okay and okay union B. Yep, answer is B, because it's basically consists of three regions. I am denoting it in three colors. First one is this black, second one is this blue here, and third one is the purple. So this region, okay, this is A, this is B. So this is what is A but not in B. So basically the common between A and B complement. This one is just the opposite. It's what is common between B but not in A. So that is A complement intersection B, and the middle one is the common between A and B. So A and B. So you can see these three here: A intersection B complement, A intersection B, and A complement intersection B. These three are mutually exclusive. So we have already seen that A union B can be written as uh, union of these three: this one, and this one. And I apply the probability according to the third axioms. As they are mutually exclusive, I can just separately take their probability measure. That is this. Fine. So yeah, as you have said, it's the second one. So let us move to our next question. It's the same again, but this time we have to find in a different manner, I guess. So let us extend the previous one, the idea here, that is P of A intersection B plus P of A intersection B plus P of A intersection B complement. Now if I want to compute P of A intersection B, how I am going to write this? This is what A complement B. So it should be, if I look at the picture once, this is A complement B. So it's whatever that is not in A and B. Okay. So therefore it's like whatever is in the B subtracted from what is common between them, and they are mutually exclusive. So since they are mutually exclusive, I can just subtract them. That is what is in PB minus PA intersection B. Similarly, for A intersection B complement can be written as what is in A, and I remove there from what is in common between A and B. So if I plug this here and plug this here, we are going to obtain PA union B as PA plus PB minus 2 PA intersection B plus PA intersection B. So you have P of A plus P of B minus PA intersection B. So this is the answer. Yeah, the fourth one. So let us look at our next question. So the level of a 4-array PAM constellation are this. Okay, there should be one more point here, that is 3 alpha, that is missing. Just need to write it down. Just a moment. Okay. What is happening? Okay, so there would be another point here, 3 alpha, but the probabilities are given. Okay, so P P of alpha minus alpha are equally probable, that is twice the probability of 3 alpha and minus 3 alpha. So this equation is given. We are also know that sum of them is equal to 1 because they all of them together constitute the sample space, and if you consider them separately they are mutually exclusive and exhaustive events. So P of alpha plus P of minus alpha plus P of 3 alpha plus P of minus 3 alpha. So let's find in terms of P alpha. So these both are equal, so there is 2 P alpha and 3 alphas are half of P alpha. So this is what P alpha, this is what is half of P alpha, and this is also half of P alpha. So therefore we have here we have 2 P alphas and here we have another P alpha. So sorry, it should be 1 here. So altogether we have 3 P alpha is equal to 1, that implies P of alpha is equal to 1 over 3, which is also equal to P of minus alpha. Similarly, P of 3 alpha and P of minus 3 alpha are 1 over 6. Now it is being said that x1 and x2 are two symbols that are drawn independently from the constellation. Okay. And what is the probability that none of the x1 x2 belong to the set minus alpha 3 alpha? So let us write down the set here first. A here is minus alpha and 3 alpha. So if I want to compute the probability here, that is probability of minus alpha plus probability of 3 alpha. So this is what 1 over 3 and this is what 1 over 6. So it should be 9 and 3 no, sorry, 9 not 9 here, 18, 6 here and 3 here, 9. So it should be 1 over 2. Okay, the probability of alpha is 1 over 2. So the probability that none of x1 x2 belong to the set is minus alpha 3 alpha. So the probability of x1 not in A is 1 minus probability of x1 in A, and that we have already found is half. So it's 1 minus half, that is essentially half. And since x1 and x2 are two symbols drawn independently from the constellation, that means they are not they are independent of each other. These two events x1 and x2 are independent of each other. Sorry, they are not events. x1 x2 denote two symbols, but if I denote first event as x1 being drawn and the second event being x2 being drawn, so they are independent as mentioned. So therefore probability of A intersection B is nothing but the product of these individual probabilities. So therefore P of x1 comma x2 not being A is equal to 1 minus probability of x, just a moment. So x1 not being in A, its probability is half, same as probability of x2 not being A. So this should be the square. So it's 1 over 4. So the probability that x1 x2 not belonging to the set happens with probability 1 over 4. Now if two events A and B are independent, then which of the following statement is always true? So you can see here probability of A union B ever in not intersection B. So probability of this should be a intersection here, because otherwise these two are A1 and 4 are exactly matching. So probability of A intersection B is equal to probability of A into B. This conclusion can be drawn also from the conditional probability here. So we have already seen in the conditional probability we can write it as P of A given B times P of B. Now when A and B are statistically independent, A and B are statistically independent, then knowledge of B does not influence A. That means P of conditional probability of A given B is same as just as probability of A only. So this is equal to P of A times PB. So we obtain from there conditional probability expression when A and B are independent. Just like the previous example we have seen that x1 and x2 are two symbols that are drawn independently, so they are not influenced by each other. That's why the probability of x1 and x2 not being in A, that is the intersection of two events, is basically the product of this event, the probability of x1 in not A and x2 in not A. So let me write it down here: probability of x1 not in A times probability of x2 not in A, since as mentioned in the question they are drawn independently or independent manner. So let us move to our next question. It is again about a 4 array PAM constellation. Again this 3 alpha point is missing with probabilities this. So these two are the sets, so we are supposed to find the conditional probability of B given A. So to solve the question, we first write down the probabilities. P of alpha is equal to 2 of P times minus alpha is equal to 2 P times 3 alpha is equal to 4 P times minus 3 alpha. And we know that sum of P of alpha plus P of minus alpha plus P of 3 alpha plus P of minus 3 alpha is equal to 1. So P of 3 alpha is going to be 2 of P minus 3 alpha. This is also going to be 2 of P minus 3 alpha, and P alpha is going to be 4 P minus 3 alpha. So if I add them down and write in terms of P minus 3 alpha, it's 4 plus 2 plus 2, that is 9 P minus 3 alpha is equal to 1. That means P minus 3 alpha is equal to 1 over 9. P of 3 alpha is equal to 1 over is equal to 2 over 9. So is P of minus alpha 2 over 9, and P of alpha is 4 over 9. So we have this set here: A 3 alpha comma alpha and B is equal to minus alpha. So probability of B given A, we have already seen, it's nothing but the probability of A intersection B given by probability of A.
Hello, am I audible now, sir?
Yes, you are audible.
Okay.
So if I compute probability of A is nothing but probability of 3 alpha plus probability of alpha, which is basically 2 over 9 plus 4 over 9, that is 2 over 3. Okay, I guess I get the numbers wrong because there is now common between A and B. So most likely either it's minus alpha in A. Okay. So in that case, A intersection B is going to be minus alpha, and its probability is going to be 2 over 9. So we have this probability 2 over 9 divided over 2 over 3 here. So that would result into 1 over 3. So the fourth one is the correct answer. Given A is minus 3A. Given A is 3 alpha and minus alpha. Let us move to our last question of today. So we have again this constellation.
Sir, will you please solve the question number 10 of assignment, or similar question like question number 10 of assignment?
Question number 10 in the current assignment.
Yes. You have a question with you, sir?
Not exactly at this moment. I need to check. Like you are talking
Uh,
about the your course assignment, right?
that is a consider the probability density function of the sample of a signal given as fm by fm is equal to sine 2m, where m is between 0 to pi 2. What is the optimum quantization level corresponding to interval 0 to pi 2?
Okay, just let me open the question once and let me check. Okay. And
Okay, sir.
and by the way, you can call me just by my name. Sir is kind of embarrassing. So,
Okay.
samples of signal. Okay, you are given an PDF, fine, sinusoid, and you are given a interval also. So, what is the optimal quantization level corresponding to a particular level? Okay, I'm exactly not getting an idea as of now, and I'm also not supposed to solve the exact question in assignment, but I will look into it and I will mail you the idea later.
Fine,
Okay.
fine. No issue. Thank you.
Okay.
Okay. So you go through the question, right?
Yeah, I go through the question while just this
Fine.
question set preparing, just because don't want any overlap between them. I just check whether these questions here are not there or not. That's what. But I went through them few days ago, so I didn't remember that. So now I only opened and I seen this one. Is there any overlap in that current set of this and the assignment questions?
Uh, some of the question yes, some of the question no.
Okay, okay. So okay, there are still overlaps. So probably I made mistake while checking them. Usually I try to change the numbers and all that. Okay, I need to be careful.
Now only one assignment is left, na? Two,
Yeah,
I think two assignment is left.
okay. Yeah, I was not very sure. Like, is it week 11, week 12 is there, or only week 11? Uh,
Week 11 is open and week 10 is open right now. 10 is a completing within on a before 2nd of April.
okay, okay,
So
okay,
then the week 11 will be there for one more week.
okay, 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 okay.
So numerical question is changed. Only the question related to the um, uh,
Theory part is changed.
definitions.
Okay, okay,
Yeah, theory
okay,
passes.
okay, 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 okay. So this question is about again having this different
But your
prob.
lecture is very helpful for us, for our community. Many people are going through this course and they are listening your recorded videos afterwards.
Yeah, I just hope so that I'm being helpful to them. Just like I'm not very
Yes.
sure I'm able to explain the things properly even, but I
No,
just
no,
try.
no, it is good actually because professor is also good. He is also explaining too well.
Yes, yes, yes.
Uh,
He explained
I'm
very
I am
well.
actually attending 3 to 4 such NPL courses,
Okay,
and
okay.
Aditya Nath sir is teaching so well.
Yes, yes, yes. He
So
is like ultimate kind of. He's very, very good.
yeah, he's very good. So in theory, but in lecture we are not able to do a discussion. It is a recorded video, right?
Yes, yes,
So
yes.
so minor query is solved in this question. This in this your lecture.
Okay, okay.
So it is very helpful. Yes.
Thanks. Like that's the kind of goal I like. I try to explain things to my best of capabilities. Sometimes I can do it. Most of the times I fail. But yeah, it's nice to hear that it's helpful to you.
Yes. So today's session is over.
No, I think I will just solve this one and
Then finish.
yeah, and then finish.
Okay.
So I'll just quickly go through it. So we have these probabilities, and some of them is equal to 1. So I'll just briefly write P of alpha plus P of minus alpha plus 4, sorry, P of 3 alpha plus P of minus 3 alpha to 1. So this is 8 P minus 3 alpha. This one here is 4P minus 3 alpha. This one is 2P minus 3 alpha. So if I add them, 8 and 4, 12, 14, 15. So P of minus 3 alpha is 1 over 15. Similarly, we have P of alpha is equal to 8 over 15. P of minus alpha is equal to 4 over 15. And P of 3 alpha is equal to 2 over 15. So we are asked about the two symbols drawn independently, fine, and none of them belonging to x1 and x2. Okay, if I denote the set as minus alpha 3 alpha, so what is the probability to belong to that set? It's just the individual sum of them, which is 4 over 15 and 2 over 15. That is 6 over 15, that can be further reduced to 2 over 5. and since this x1 and x2 are drawn independently, so that probability of x1 and x2 not belonging to alpha is actually statistical independent event. So I can just take the product of x1 not belonging to alpha and x2 not belonging to, sorry, not alpha, a. So this is basically the probability of x1 not belonging to a, whole square of that, that is 1 minus probability of x1 belonging to a whole square. So this is 1 minus 2 over 5 whole square, that is a 3 over 5 and 9 over 25. So the second one is the answer. So with that, I plan to conclude today's session. If you
Yes. So thank you. And if it is possible, stop the recording. Then we'll discuss something.
Okay, okay, sure. Just a moment.